Under Pressure, Part 1, Just the Facts, is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. Under the Pressure, Part 1 discusses what pressure or force per unit area is, how you use it, and some of the methods for measuring it. Part 2 continues the discussion with atmospheric pressure, barometric pressure, gauge pressure, absolute pressure, and vacuum pressure. Pressure is one of the most common variables in chemical processes, and understanding how to use it is fundamental to chemical and thermal processing. Pressure is defined as a normal force per unit area with SI units of the Pascal. 1 Pascal is equal to 1 Newton per meter squared. Another common unit is a torr or millimeter of mercury. In 2019, the torr and the millimeter of mercury were both redefined. As a result, the torr and the millimeter of mercury are no longer identical, but they differ by less than 1 part in 7 million. So for anything that we're going to use them for, they are interchangeable. Just remember to look up the difference before you interview for a job in this. Additional common pressure units are the standard atmosphere or atmosphere, the kilopascal, the bar, and the pounds per square inch. For helping conversion among the common pressure units, remember that 1 standard atmosphere is equal to 1.01325 bar, or 101.325 kilopascal, or 101,325 pascals, as well as 760 torr and 14.6959 psi. A common source of pressure is the height of a column of fluid. This pressure is called the hydrostatic pressure. The pressure at a given depth in the fluid is the pressure at the surface of a fluid plus the weight of the column of fluid from the surface to the depth of interest. The derivation is easiest with an incompressible liquid, where the density doesn't change with pressure. Liquid water is reasonably close to an incompressible liquid. Let's calculate the weight of a column of water at depth h and a cross-sectional area of A, which is pi d squared over 4 for a cylinder. We'll call the pressure at the surface of the water P0. The density of water is rho. The mass of the water is the density times the volume, rho times A times h. The weight or normal force at depth h is mg. The normal area at the bottom of the column is A. The change in pressure is the weight mg divided by the area A. Simplifying, the change in pressure, delta P, is mg over A, or rho AHg over A, or rho GH. Written in terms of the pressure, P equals rho GH plus P0. A consequence is that the pressure does not depend on the geometry of the column, just the depth of the fluid. Since the change in pressure is linear with the depth, there are a number of pressure units defined in terms of the hydrostatic pressure of that height of fluid. For example, a millimeter of mercury, an inch of mercury, an inch of water, a foot of water, or a meter of water. 1 atmosphere is about 34 feet of water, or 10 meters of water. Draft pressure in heating, ventilation, and air conditioning systems are often given in inches of millimeters of water. Manometers use hydrostatic pressure for pressure measurements. If we add up the hydrostatic pressures from P1 to P2, we have P1 plus rho Ag times H2 plus H1 equals rho BgH1 plus rho CgH2 plus P2. Or solving for delta P equals rho BH1 plus rho CH2 minus rho A times H1 plus H2, and the whole thing times G. For the most common case of rho A and rho C being equal because they are the same fluid, such as for measuring a pressure drop in a pipe carrying water or air, then delta P is just rho B minus rho A times GH1. So delta P is linearly related to H1. Now, let's see an example of a typical calculation involving hydrostatic pressure. We will begin with a diagram that is obviously not to scale because the 20 centimeters tall piston is just a little bit shorter than the 19.28 foot column of benzene, and the 2.078 meters of argon is shorter than the 7.480 inches of mercury. The problem reads, a cylindrical piston of an unknown solid rides atop a column of benzene inside a cylinder whose top end is open to the atmosphere and whose bottom end opens into a reservoir of mercury. Attached to another part of this mercury reservoir is a cylinder whose top is sealed and whose bottom opens into the mercury reservoir. Above the mercury in the second cylinder is a 1 gram mole of argon. We discussed gram moles in What is a Mole video at a pressure of 1.493 bar absolute. We'll discuss absolute in part 2. Because the argon gas is so much less dense than any of the fluids, we can ignore the change in hydrostatic pressure in the gas and treat it as being at a constant pressure. The, again, not to scale, dimensions of the cylinder and columns are given in the drawing. The entire system is at 68 degrees Fahrenheit. What is the density of the unknown solid used to make the piston? The data we have are that the density of benzene is 879 kilograms per meter cubed. The density of mercury is 13,546 kilograms over meter cubed. And the local atmospheric pressure above the piston is 1 standard atmosphere. We'll start the solution with a diagram. Because the mercury completely fills the horizontal reservoir, the pressure at the bottom of the two columns must be equal. Also, as a reminder, the change in pressure from the top of a column of fluid to the bottom is ρgh. Anyway, since the pressures at the bottoms of the two columns of fluid are equal, we can just add them up and set them to be equal. P atmosphere plus delta P piston plus delta P benzene must equal delta P mercury plus P argon. Substituting in, the only unknown is the density of the piston, although we do have a number of unit conversions to make. We'll assume you watched the dimensional equations video and have no trouble with the unit conversions. If you convert all of the heights to meters and use g in meters per second squared, then all terms are in Pascal. Solving for the density of the piston gives you 11,500 kilograms per meters cubed, or 11.5 grams per centimeters cubed. Here we have a spreadsheet of the solution. G is the standard value of the gravity constant. The pressure of the argon is given in bar and Pascal. The atmospheric pressure is in Pascal. With the density of the benzene in kilograms per meters cubed, we have the height of the benzene first in feet, then in inches, then millimeters, and finally in meters. The ρgh formula gives the pressure of the column of benzene as 50,656 pascals. A similar process for the mercury gives the height in inches, then millimeters, which incidentally is millimeters of mercury or torr, and finally meters, which by ρgh gives us the pressure of mercury is 25,239 pascals. We could also have done this calculation by using the conversion that 760 millimeters of mercury is equal to 1 atmosphere, or 101,325 pascals. We then calculate delta P of the piston, from which we get that the density of the piston is 11,501 kilograms per meters cubed. There is no reason to carry that many significant figures, so 11,500 is quite sufficient. There is a copy of the spreadsheet on the website if you want to look at the actual formulas in the cells. The key takeaways from this video are: 1. Pressure is the second most common process variable to measure. 2. Hydrostatic pressure for an incompressible fluid is calculated as the density times G times the fluid height or depth, written as ρgh. 3. Manometers measure delta P's with hydrostatic pressure. Thanks for watching. This video was brought to you by the DOFPro team.